Assalamu alaikum dear students, I am engineer Abdul Basit and we are in week number 4, lecture number 1. Okay, so this is basically part first of this week number 4 lecture. Okay, as we all know, we have started a new subject, that is hydraulics. Okay, for BE electrical engineering and for civil engineering as well. Okay, this topic that we are going to cover today is classification of fluids. Okay, so before going in details about the classification of fluids, let me remind you that in previous few lectures we have discussed few terminologies of fluid mechanics and hydraulics, and these terminologies were actually a starting for this classification of fluid as well. Okay, so let's talk about the classification of fluids. So basically we are going to discuss these four types of fluids, that is ideal fluid, Newtonian fluids, and non-Newtonian fluids, and real fluids as well. Okay, so basically the fluids can be classified into four types depending upon the presence of viscosity. Okay, first of all, ideal fluids. So the definition shows that a fluid having no viscosity. As the name indicate that ideal refers to those fluids which are ideally possible, not practically. Okay, so having no viscosity is not an option in fluids. In fluids we should have some viscosity of that particular fluid. Let us consider the least viscosity fluid, that is alcohol. Okay, it is having the least viscosity, or you can say is having less viscosity as compared to water as well, but it do have some viscosity. Okay, so you cannot consider any fluid as having no viscosity. Okay, so a fluid having no viscosity is known as ideal fluid, so which is in actual practice there is hardly any ideal fluid, as every fluid has some viscosity. Thus it is only a theoretical case. So this is just a theoretical case which can be used for numerical evaluation or for some equation derivations. Okay, so this may be the case, otherwise there is no fluid like to having no viscosity. Then let's talk about the real fluid. So real fluids are actually those fluids which are having no viscosity, is known as real fluids. So I think the definition is a bit wrong. Real fluids are having some viscosity. In actual practice, the fluids meet with the engineering science are real fluid. Okay, real fluids do have some viscosity. It's not like no viscosity. The definition is a bit wrong. A fluid having some viscosity is known as real fluids. So in actual practice, all the fluids are real fluids, and they do have some viscosity. Okay, now let's talk about the Newtonian fluid. So simple words, I can say that those fluids which do have do follow the Newton's law of viscosity are called Newtonian fluid. Okay, and those fluids which do not follow the Newton's law of viscosity are called non-Newtonian fluid. So that is quite simple. Okay, so we have already discussed this in Newton's law of viscosity. A fluid which obeys the law is termed as Newtonian fluid. Mathematically, shear stress will be equal to velocity divided by y, which is the distance between the layers. Okay, so in other words, you can replace that, you can take that shear stress in the Newton's law of viscosity equation. So that will be the absolute viscosity for you, that shear stress multiplied by y divided by v. Okay, in other words, a fluid whose viscosity does not change with the rate of deformation or shear strain. Okay, so this is something quite interesting, or you can say like discussing in other ways, that is like one definition for Newtonian fluid is those fluids which obey the Newton's law of viscosity. So that is simple. Okay, and the other definition should be that those fluids whose viscosity does not change with the rate of deformation or strain. Okay, if a fluid is going under some strain or some deformation due to some applied shear force, so its viscosity will not be affected. So such type of fluid are called Newtonian fluid. Otherwise, For those fluids which are whose viscosity is changing with the change in deformation, or with the rate of deformation, or shear strain, are actually called non-Newtonian fluid. Okay, so if we draw a graph showing shear strain is on abscissa and stress on ordinates, so this is that graph. Okay, shear stress is shown over here on the abscissa, and a shear strain on the ordinate, that is tau. Okay, so if you see here that the shear stress is increasing along the x-axis, so if the shear stress is increasing and at the same time the shear strain is increasing, so there is no much difference in the relationship between, this is a straightforward linear relationship between shear stress and shear strain. But in case of non-Newtonian fluid, that relationship is not that linear relationship. Okay, it's a 2-degree curve where you can see that the shear stress is increasing and at the same time shear strain is increasing. So up to some point, up to some extent, it is giving us a bit linear relationship, but after that the relationship is changing, and you can say that more shear stress is required to produce the same shear strain. Okay, so then you can say that the viscosity is affected. So such type of fluid is called non-Newtonian fluid. Okay, so here is the definition as well. A fluid which does not obey Newton's law of viscosity, this is the first definition, are called non-Newtonian fluid. And in other words, a fluid whose viscosity changes with the rate of deformation or strain, shear strain, so shear strain, is known as non-Newtonian fluid. So these are the two ways to discuss it. Okay, then coming to the classification of fluids regarding its types of flow, okay, or viscous flow. So viscous flow may be classified into the following two types depending upon the factors whether the viscosity is dominating or not. Okay, so simple, you can say whenever a fluid is flowing through a pipe or through any duct, okay, and there is an interruption in the way, okay, and still the fluid particles are following its own path, and the path of the fluid particles do not cross each other, so such type of flow is called laminar flow. As you can see in this figure, that this one red line is showing us the flow path of one particle. Okay, then this arrow is showing the second particle, this is the third, fourth. So in practical we may have many particles, millions of particles, but here in the diagram we are just showing here 5 particles. Okay, so each particle is following its own path in a straight line. Okay, and they are not crossing each other. So such type of flow is basically termed as laminar flow. And turbulent flow is actually that type of flow in which the particles, the path of the particle flow will cross each other or will not be in the straight line whenever there is an interruption between for the flow of the fluid. Okay, so such type of flow is called turbulent flow. Okay, so in simple words you can say it is a flow in which the viscosity of fluid is dominating over the inertial force. It is more or less theoretical flow, which rarely comes in contact with the engineers and is also known as a viscous flow. So laminar flow may be also termed as viscous flow, in which the one definition is all the particles of the fluid will flow its own path and will not cross each other's path. So that will be a laminar flow. This is one definition. And the other definition is the viscosity will be a dominant factor as compared to inertial force. So inertial force is actually the particle want to flow in a straight line. This is inertia. Okay, or want to keep a state of rest or state of motion. So this is inertia. Okay, so inertial force is not dominating, viscous force is dominating, because the particles are like following a straight line. Okay, a straight line, and the inertial force which is trying to interrupt its flow, okay, that is not dominating. So in that way case you can say this is a laminar flow. So it is not practically possible, or you can say it's a theoretical type of concept like ideal fluids. Okay, for equation derivations, for mathematical calculations, you can use this type of flow. Okay, because this will be easy to deal with. But actually we are having this type of flow in all cases, whether this is a flow of stream, whether this is a flow of water in pipes, whether whatever that type of flow is, that will be a turbulent flow, not laminar flow. So this is practical case, turbulent one, and that laminar is not a practical case. This is a theoretical one. Okay, so classification of fluids, as we were discussing, laminar flow. Laminar flow can be best understood by the hypothesis that liquid moves in a form of concentric cylinders, slides one within the another one as shown. Okay, the concentric circles, laminae, such a flow which takes place at a very low viscosity is known as laminar flow. Okay, so you can say here you can say that this is a simple example of the laminar flow. For example, we are having different layers of the fluid flow, and these layers are in the form of cylinders which are wrapped around each other. Okay, as shown in this figure. Okay, and whenever the flow is there is a flow of fluid in this pipe, this is externally, this external one is a pipe. Okay, so when the fluid is flowing through this pipe, so all the layers will follow its own path. Okay, so this cylinder is flowing in its own path, this one is in on path, this one is on. But in case of laminar flow, this will be the case. Okay, all the particles are not following its own path, and this is the practical case which is called turbulent flow. Okay, so that is, I think, quite clear now from this definition. Then coming towards the turbulent flow, so again inertial force is dominating as compared to the viscous force. Okay, it is a practical flow which comes in contact with the engineers. You can say this is that type of flow which are in practical case it is possible, and engineers do use this type of flow for their practical purposes. Okay, so in this case the flow concentric circles or cylinders diffuse or mix up with each other. Okay, and the flow is disturbed one. Such flow which takes place at a high velocity is known as turbulent flow. Okay, so you can say these cylinders which are flowing in its own path in case of laminar flow will not flow in its own path in case of the turbulent flow. Okay, these cylinders will mix with each other, and that will be a disturbed type of flow. Okay, and that flow will be called then the turbulent flow. Okay, in other words, there is a term called the Reynolds number, which can differentiate the turbulent and laminar flow. Okay, with the help of this mathematical number, this digit. Okay, this number is actually showing us whether this fluid is flowing in a turbulent manner or in a laminar manner, or this is in transition zone. So transition zone actually refers to that zone when the laminar flow is converting to the turbulent flow, or turbulent flow is converting to the laminar flow. So the zone in between these two types of flow is called transition zone. Okay, what is Reynolds number and what does it mean by this 4000? Okay, how this can be calculated, so this will be discussed in the second part of this week number 4 lecture. Okay, we will discuss it later on. Then coming towards critical velocity. Critical velocity is something you can say is the same type of a term like laminar and turbulent flow. Okay, how we can define it? It is a velocity at which the flow changes from the laminar flow to turbulent flow. Okay, so you can say the velocity at that transition zone, at this transition zone, whenever the laminar flow is changing to the turbulent flow, so there will be a transition zone in between where you cannot classify this type of flow either a turbulent flow or laminar flow. It will be in between these two. Okay, so that will be a transition zone. So the velocity of fluid in this transition zone is actually called uh, critical velocity. Okay, so the critical velocity may be further classified into two types: lower critical velocity, upper critical velocity. Okay, so what does it mean by lower critical velocity? It has been experimentally found that when a laminar flow changes into turbulent flow, it does not change abruptly. Okay, the velocity is like laminar flow and turbulent flow are not abruptly changing in each other. Okay, there will be a transition zone, there will be a lengthy transition zone in between them. Okay, so as I was discussing, then but it has got some transition period between the two types of flow. So this is already discussed. Thus a velocity at which the laminar flow stops, or in other words, velocity at which the flow enters from laminar to transition period, is actually called lower critical velocity. So from laminar to transition zone, the velocity will at that point when the laminar is transferring to the transition zone, so that velocity is actually called lower critical velocity. And when I explain this upper critical velocity, so both the terms will be more clear to you. A velocity at which the turbulent flow starts. So you can say that the velocity in between the zone of transition in turbulent, that is called actually the upper critical velocity. And at the zone between laminar and transition, that is called lower critical velocity. So at which the velocity enters from transition period to turbulent flow is known as upper critical velocity or higher critical velocity. So let me show it from here. You can say, let me try it for you as well. So here it is, the transition zone. Okay, this is the transition zone, which is the zone in between laminar and turbulent flow. Okay, so between the laminar and turbulent, this is the point at which the velocity will be the lower critical velocity. Okay, and this is the zone between transition and turbulent at which the velocity will be the upper critical velocity. Okay, so this was the thing I was trying to mention here. Okay, that's all from this lecture part 1, week number 4. So in the next part we will discuss about the Reynolds number and how we can differentiate different types of flow, laminar flow and turbulent flow, with the help of Reynolds number, and how we can determine the Reynolds number as well. Okay, thank you very much for now.